In this lecture, we would like to consider some theorems of elasticity. There are number of theorems which are very useful, and we would like to consider some of them. First one is uniqueness theorem, principle of superposition, method of virtual work and minimum potential energy principle, Castigliano's theorem, Maxwell-Betti reciprocal theorem, complementary energy principle, and we will also consider some problem solving using some of them. So, let us consider first uniqueness theorem. In the uniqueness theorem, what is indicated is the following. For a body subjected to a specified system of loading, there can be one and only one set of stress distribution. That means, if you have a body and it is subjected to loading like this, at its boundary it can also be subjected to body forces like x and y in 2 dimensions. And if you indicate the loading, boundary loading by P1, P2 and so on, for this specified set of loading P1, P2 etc. and x and y, the stress distribution in the body is unique. There cannot be two possibilities. Let us consider that there are two possible solutions, and these sets are represented by sigma x dash, sigma y dash and tau xy dash. That is the first set, and let us also consider that there is another set possible which is indicated by sigma x dash, sigma y dash and tau xy dash. And these two sets, they correspond to the boundary tractions, let us say x and y, and the body forces x and y. Since these are the solutions, then we must have delta sigma, they will be satisfying the equilibrium equation. So, therefore, delta sigma x dash delta x plus delta tau xy dash delta y plus x equal to 0. Similarly, we would have delta tau xy dash delta x plus delta sigma y delta y plus y equal to 0. And since the second set is also the solution, we would certainly have delta x double dash delta x plus delta tau xy double dash delta y plus capital X equal to 0 and delta tau xy double dash delta x plus delta sigma y double dash delta y plus y equal to 0. And at the same time our boundary tractions must be related. If the boundary direction cosines at a point is L and M, then Sx must be equal to L into sigma x plus M into tau xy dash. So, Sx is L into sigma x dash plus M into tau xy dash. Similarly, Sy is equal to L into tau xy dash plus M into sigma y dash. Now, second set is also going to satisfy similar conditions. L into sigma x double dash plus M into tau xy double dash is Sx and Sy is equal to L tau xy double dash plus M sigma y double dash. Now, let us try to subtract the second set of equations from the first set. First the equilibrium equations, then we will also consider the boundary conditions. So, therefore, if we do that, if we subtract this equation from this one, that is going to give us delta delta x sigma x dash minus sigma x double dash delta delta y tau xy dash minus tau xy double dash is equal to 0. Similarly, we will have delta delta x tau xy dash minus tau xy double dash plus delta delta y sigma y dash minus sigma y double dash equal to 0. So, therefore, we get a new set of solutions which is given by difference between the two sets, which corresponds to a loading condition where there is no body force. Similarly, we are going to get now Sx equal to 0 for this arising out of the two set. We will have Sx equal to 0, which is given like this. Similarly, Sy is also 0 arising out of the two set, a new set of stresses. So, we find that this set sigma x dash minus sigma x double dash, similarly tau xy dash minus tau x dash xy double dash, they corresponds to a set of loading wherein x, y are 0, so also Sx, Sy are also 0. So, the new set of solutions, or rather new set involving sigma x dash minus sigma x double dash and sigma y dash minus sigma y double dash and tau xy dash minus tau xy double dash, they corresponds to a set of forces wherein the body forces are 0 and also boundary forces are 0. Now, let us try to look into the strain energy of the whole body and its form. The strain energy can be written in a form like this. So, the expression for the strain energy in the whole body is given by integration of 1 by 2 E by 1 plus nu into nu by 1 minus nu into x epsilon x plus epsilon y whole square plus epsilon x square plus epsilon y square plus gamma x y square, and this integration is to be done over the whole volume. What we find here, that the expression is such that irrespective of the sign of the strains, we are going to get the strain energy density. This indicate the strain energy density positive, and if the strain energy of the whole body is to be 0, we must have each of the strain components 0. Now, the strain energy density, so strain energy density is 0, and that will make the total strain energy 0. U will be 0 only when strain energy density is 0, and this also indicates that this is indicating a situation that epsilon x equal to 0, so also epsilon y, so also gamma xy. Now, when we do not have any external loading on the component, the work done on the component in deforming is 0, and therefore, the strain energy of the body is 0, and it would indicate that if the strain energy of the body is 0, this relationship indicates that it is possible only when the strain at each and every point of the body is 0, and therefore, this will mean that these, since strains are related to the stresses, if the strains, all the three components of strains are 0, that would mean that sigma x dash minus sigma x double dash, that is also 0. So, that means that sigma x dash is equal to sigma x double dash. So, by the same argument, we will find that the two sets will finally give rise to a situation like this, that the normal stress in the x direction in the two sets are equal, so also the shear stress are equal. So, hence we have only one solution. So, the two sets that we have assumed, they are only one set, they are equal, and hence we cannot have two solutions to a problem. So, this is the proof of the uniqueness theorem. So, finally, what we found is that if you are given the loading on a body specified, for the set of loading specified, you can have one and only one set of solution for stresses. Now, we would like to consider this second theorem, which relates to principle of superposition, which is concerning superposition principle. If you have a body and it is subjected to two sets of loading, then the stresses for each set of loading can be added together to get the stresses corresponding to the two sets together. I repeat again, if you are given a set of loading, you will have a set of stresses, and if there are two sets of loading on the body, then you can get two sets of stresses, and if you apply the two sets together, the stresses that are going to come up will be also obtained by adding the set of stresses together. So, we would like to prove this, and this is really possible because the system is linear. So, let us consider that we have this set of stresses sigma x1, sigma y1 and sigma and tau xy1. So, this is tau xy1, and this corresponds to the forces Sx1, Sy1 and body forces x1, y1. Similarly, let us consider that sigma x2, sigma y2 and tau xy2 corresponds to set of forces which are Sx2, Sy2 and x2, y2. Now, this set of stresses are going to satisfy the equilibrium equations. We can write now in tensor notation sigma ij comma j plus xi 1 is equal to 0 for the first set. So, also we will have Cauchy formula Lj sigma ij 1 is equal to Si 1. So, this is the boundary traction. Similarly, we have sigma ij comma j superscript 2 is going to be xi superscript 2 equal to 0. Simultaneously, we will have the Cauchy formula Lj sigma ij2 is equal to Si2. So, these are the two sets. Now, if we apply the two sets of loading together, then the stresses can be directly added and we get the total stresses. So, this is now can be shown like this, that if we add the two sets of these two set of equations, then we are going to get delta xj sigma ij1 plus sigma ij2 plus xi1 plus xi2 is equal to 0, and similarly if we add the tractions we get Lj sigma ij1 plus sigma ij2 is equal to Si1 plus Si2, and finally if we write the total stresses sigma ij, and this is the total traction x, and here this is the total traction, this is the total boundary force, I beg pardon, total body force x, and this is the total traction. Then finally we find that this equation is nothing but delta xj sigma ij plus xi equal to 0, and we have Lj sigma ij Si, and therefore your stresses sigma ij corresponds to the sum total of the two sets of loading. So, therefore, the principle of superposition is valid because the governing equations are linear equations. Now, we would like to consider method of virtual work and minimum potential energy principle. Before I go into considering the method of virtual work and minimum potential energy principle of elasticity, I would like you to reconsider some of the things which you have done in your mechanics course, the method of virtual displacement and method of virtual forces. These are principles which are very useful and which are applicable to both rigid body system and deformable body systems, and they are useful in finding out sometimes unknown forces and sometimes unknown displacements. So, in the case of method of virtual displacement, you can consider this principle or method of virtual displacement for the calculation of unknown forces. So, if you remember that mechanics, you must have considered a situation like this. There is a rigid beam, let us say AB, and it is subjected to some loading P at C. If you are interested in finding out the reaction at B, one can consider the method of virtual displacement. One can apply the displacement to the load by some amount, and if we consider the displacement of the whole beam in conformity. So, if this point displaces by delta, then this B point is also going to displace by some amount, keeping the geometry straight. Therefore, the displacement here is going to be 2 times delta at the other end, and therefore, we have the reaction force which is RB here, that is going to move over a distance of 2 delta. And if we assume that AC is equal to CB is equal to L by 2, then according to the method of virtual displacement, the work done, sum total of the work done by the external and reactive forces is equal to 0, or the work done by the external forces is equal to the work done by the reactive or internal forces. So, in this case we have the external force P doing an work, P will do the work while it is moving from C to this point by delta. The work done by the load is P delta, and at the same time this reaction RB is moving by a distance of 2 delta, and therefore, since the movement is in the opposite direction, the work done is negative, and therefore, RB into 2 delta equal to 0, and this is the sum total of the virtual work, and this is 0, and that gives you directly RB equal to P by 2. So, this is the method of virtual displacement. Herein we have been able to calculate the reaction by applying the virtual displacement. Now, we can also have the method of virtual forces, wherein we apply the virtual forces and try to equate the internal work with the external work and calculate the unknown displacement. I would like to illustrate this principle by considering this simple example. Let us consider that we have 2 springs connected in series like this. Let us consider that they have stiffnesses K1 and K2, and at this point we are applying a force equal to P. Now, we are interested in calculating the deflection at this point U. To consider the method of virtual forces, we now consider that the same system here let us now apply a virtual force of magnitude equal to small f, and therefore, this force is acting on each of the springs, and the work done by the virtual force on the displacement, real displacement u. So, that is the external virtual work. So, external work is equal to F into u, as if that this virtual force has moved by a distance of u, and this work will have to be equated with the internal work, and that internal work is nothing but internal virtual forces doing work on the real displacement of the elements. So, this force which is externally applied, it is acting on each of these springs. So, therefore, the deflection of the spring number 1 is nothing but P by K1, and therefore, the virtual work done by the virtual force is nothing but F acting in the spring on the displacement P by K1. So, therefore, the first spring would have virtual work is equal to P by K1 into F. Similarly, the second spring would have displacement equal to P by K2, and therefore, the virtual work is P by K2 into F. So, therefore, the sum of the two virtual works will give us the total internal work, and when we equate these two, we get this real displacement of this point of application of the load, which is given by P by K1 plus P by K2. So, therefore, that is the total displacement. So, these two principles are going to be useful even when we are considering the proof of the sum of the principles here. Now, according to method of according to the minimum potential energy principle, for a system rigid or elastic in equilibrium, let us consider the method of virtual work. We would like to define it. For a system rigid or elastic in equilibrium, the sum of work done by external and internal or reactive forces on a set of virtual displacement is 0. So, the method of virtual work is stated like this: for a system rigid or elastic in equilibrium, the sum of work done by external and internal or reactive forces on a set of virtual displacements is 0. So, let us consider let me first write this principle. For a system rigid or elastic in equilibrium, the sum of work done by external and internal or reactive forces on a set of virtual displacements is 0. So, let us consider a configuration like this. The body is in 3 dimensions, and let us assume that the external forces are x, y, z, and the boundary tractions are sy, sx, sy and sz, and herein the forces gives rise to stresses which are nothing but internal forces. So, we call them internal forces, those are reactive forces. So, that is sigma x, sigma y and we will have the 6 components up to tau zx. Let us apply a set of virtual displacements. That means, in this case the virtual displacement is given over the whole of the body. Let us say that this set of virtual displacements let us represent them by delta u, delta v, delta w. Now, these virtual displacements are going to give rise to virtual strains we will have delta epsilon x, which is nothing but delta u delta x. Similarly, we can write all the components up to gamma zx, which is delta w delta x plus delta u delta z. So, these are the strains. Now, external work done will be now given by, we have x into delta u plus y into delta v plus z into delta w, and this is integrated over the whole volume. This is the volumetric work, and then we have the surface forces Sx also doing work on the displacements delta u, delta v and delta w, and it has got to be integrated over the whole surface. The internal work is equal to minus sigma x, because they are reactive forces, the work done will be negative. So, sigma x into delta epsilon x, and all the 6 product terms will come, and the last term would be tau zx delta gamma zx, and this is going to be integrated over the whole volume. Now, according to virtual work principle, therefore, we will have the sum total of the external and internal work equal to 0, and therefore, now we can write that v integration over v sigma x delta epsilon x tau zx delta gamma zx dv minus v x delta u z delta w dv minus sx delta u up to sz delta w ds, and this is equal to 0. So, therefore, the sum of these expression will have sum of this equal to 0. So, this is the final outcome of the application of the virtual work principle. So, we have obtained this relationship, and we can now rewrite the expression like this. We had integral v sigma x delta epsilon x plus up to tau zx delta gamma zx, and this is integrated over the volume, minus x delta u plus y delta v plus z delta w integrated over the volume, and then this surface forces multiplied by the corresponding displacement integrated over the surface. Now, this expression, this can be written in a form integral delta sigma x epsilon x up to tau zx gamma zx minus v delta x u z w dv minus s delta sx u sz w ds equal to 0. So, therefore, we can take this delta out. This is because of the fact this is a variational symbol, and if we have variation of delta x multiplied by epsilon x, this is nothing but delta sigma x epsilon x. It is like differentiation of product of two functions. We can write first differentiation of the first keeping the second constant, and then we can differentiate the second keeping the first constant. So, that is the way we can do. Now, in this case, since the stresses are constant sigma x, sigma y, sigma, this variation is 0, therefore, this product is 0, and hence this quantity is equal to sigma x into delta epsilon x. That is what has been made use of in writing the expression from this to this step. Finally, this delta operator can be taken outside the integral sign, and we can now write that this is nothing but delta integral v sigma x epsilon x delta zx gamma zx dv minus v xu dv plus sx u plus sz w ds, that is equal to 0. Now, this expression here is nothing but the strain energy. So, therefore, this is nothing but delta of u, and this is nothing but the external work done. So, therefore, this is nothing but delta of w, and that is equal to 0, and we can write this thing as delta of u minus w equal to 0, and this is nothing but strain energy minus the work done by the external forces is nothing but potential energy. So, therefore, delta pi equal to 0, which indicates that it is nothing but if the body is in equilibrium, its potential energy is stationary. It is either maximum or minimum. So, in general, or since the body has got to be in equilibrium, the potential energy is stationary at equilibrium position, and therefore, this follows from virtual work principle. So, the virtual work principle leads to the minimum potential energy principle of elasticity. So, what it finally gives rise to, that if a system, if an elastic system subjected to set of external forces is in equilibrium, then the potential energy of this system is stationary, and this principle is a is obtained from the consideration of method of virtual displacements. Now, we would like to consider some other theorems. Before we can do that, we must introduce what is known as complementary strain energy. You consider a component which is loaded like this, now if we consider that this point is having a displacement equal to u when the other point is fixed, we can plot the load versus deflection diagram. If we plot it for elastic body, which need not be always linear, we can get a variation like this. So, in this direction we plot load, here it is displacement. Now, if we have loaded the body up to a state, let us say here, where the final load is Pf and the final deflection is Uf, then in that case, while we have loaded the body gradually, we have done some work, and this work done is given by the area under the load deflection diagram, and therefore, that is U. U can be obtained by integrating the quantity P into du. So, therefore, if you consider the integration of this quantity, where this is du and this height is P. So, if we integrate this quantity, that gives us the strain energy of deformation, and it is called potential energy of deformation. On the other hand, if we consider the area which is bounded by the y axis and the diagram, which can be obtained by considering, we can consider integration of this area, let us say this is dp. So, if we integrate this quantity, that is 0 to Pf u dp, then we get a quantity which is indicated as u star. It is called complementary potential energy. So, this is complementary, this total area is the rectangular area, and we have this potential energy plus complementary energy is equal to the area of this rectangle. If the system is linearly elastic, then in that case we will have the load deflection diagram going to be like this. So, if you have loaded it up to, let us say, level Pf Uf, then we will have the strain energy is given by this area, which is u, and at the same time we are going to get the complementary potential energy given by the area above, which is u star, and in this case u equal to u star. So, therefore, the complementary potential energy and the strain energy is equal in a linear system, whereas in the case of nonlinear system, the complementary energy and the potential energy of deformation are different. Now, looking into this relationship that we have written there, u star equal to integral u dp, we can now write, if we differentiate both sides, what we find is that du star dp is equal to u. So, if you differentiate the complementary potential energy with respect to the load, then you are going to get the deflection along the line of action of the load, or deflection of the point of application of the load. So, this is nothing but Castigliano's theorem, which states that the deflection of the point of application of the load is given by the derivative of the first derivative of the complementary energy with respect to the load. In case you have a system wherein there are number of loads acting, then in that case the complementary potential energy is going to be a function of number of all the loads. So, therefore, here it is going to be function of all the loads applied. Then in that case one can write the deflection along the line of action of a force Pi given by partial derivative of the complementary energy with respect to the load Pi. So, herein you have to take the derivative of the complementary energy with respect to the load for which you are interested in calculating the deflection. In the case of linear elastic system, since u equal to u star, we find that this u along the line of action of the load Pi is going to be also given by delta u delta Pi. So, the deflection along the line of action of a force is given by delta u delta Pi. So, for a system with number of forces acting, the deflection is given by the partial derivative. We would like to consider the proof of this theorem. So, Castiglione's theorem, you will just make simple symbol here, ui equal to delta u star delta Pi. Let us consider a body which is fixed at the 2 points like this, and it is subjected to a number of external loads P1, P2, P3 and so on. Let us say there are n number of forces. Now, if we apply all these loads gradually and bring to their final level, then we would have some energy input to the system, and that energy input to the system, if the system is linear elastic, then in that case that strain energy is equal to u, and that is also equal to u star, and this is equal to half P1 U1 half P2 U2, and it has got to be considered up to the last load and the deflection. So, therefore, the strain energy is nothing but half P1 U1 plus P2 U2 up to Pn Un. Now, let us consider that a typical load Pi is increased by delta Pi. So, we had the load Pi and now it is increased to P plus delta Pi, keeping all other load constant. So, therefore, we do not have any increment in the other loads they are all 0. So, we just hold the loads constant except this Pi, which is increased by delta Pi. So, if we do that, what is going to be the change in the complementary energy of the system? That is going to be complementary energy of the system is going to change because of this change in the load, and it is nothing but Ui into delta Pi. Let us understand this. If we consider the deflection of each of the load point like P1 U1, we would have got the deflection like this after it has reached the level P1. Similarly, if we consider the load Pi, after we have reached the level Pi, we would have got the deflection given by Ui, and this is the variation of the deflection. Similarly, we will have Pn varying with displacement like this, and now what we are trying to do, we increase the load Pi by a small amount delta Pi, and this is going to cause some changes in the deflection here. So, it will cause some changes in the deflection, and the other loads are going to remain constant, but they will undergo some deflection. So, therefore, there will be some change in the deflection. So, therefore, there will be some additional area under the load deflection curve. Similarly, this load would have also undergone some more deflection. So, therefore, there is going to be some work which is going to be represented by this area. Now, since there is no increase in the area between the load deflection diagram and this axis, therefore, this change is 0. So, also the change in this area between the load deflection diagram and the vertical axis is 0. There is only a change in the area here, and this area is nothing but, if you consider the deflection here at this point is Ui, then this change in the area is approximately Ui into delta Pi. So, therefore, change in the complementary energy comes up because of the load delta Pi alone, and therefore, this is given by this, and therefore, we have Ui equal to delta U star by delta Pi. So, if we consider the limit as delta Pi tends to 0, we have Ui equal to delta U star by delta Pi. So, therefore, the deflection along the line of action of the load Pi is given by the partial derivative of the complementary energy with respect to the load, and since in the linear elastic system U star equal to U, therefore, we can write that is also equal to delta U delta Pi. So, this is the proof of Castigliano's theorem, that if you consider the energy of the system in terms of the loads, then you take the derivative of the energy, strain energy in terms of the load, that will give you the deflection along the line of action of the load.